Let's do a couple of examples of changing variables. So here's the first one. Here's the first one. Suppose we want to calculate the double integral over the domain D of the function arctan of y over x dx dy. What do I have to still tell you? What is D exactly? Where D is the domain bounded between x squared plus y squared equals 1, x squared plus y squared equals 4, y equals x, y equals root 3 times x, and x is greater than or equal to 0. Okay, so the first thing we have to do is, it's obvious what the function is. Let's understand what this domain is. So what is x squared plus y squared equals 1? That's a circle of radius 1 centered at the origin, right? Likewise, x squared plus y squared equals 4 is a circle of radius 2 centered at the origin. Everybody knows that, right? Y equals x is a straight line, right, with slope 1 going through the origin. Y equals root 3 of x is again a straight line going through the origin with a slightly bigger slope. So if y equals x is this, y equals 3x is this. And then we are only looking at non-negative x's. Do you agree? Let's draw. Let's draw D. So D is going to look something like this. Here's a circle of radius 1. Here's a circle of radius 2. Here's y equals x. Here's y equals root 3 of x, something like this. So let's label everything. So this is y equals x. This is y equals root 3 x. This is x squared plus y squared equals 4. This is x squared plus y squared equals 1. And we want the domain which is bounded by these 4 things, where x is greater than or equal to 0. So the domain we're looking at is this thing. It's between the two circles, so it's in the ring. It's bounded between these two lines, so it's either this or this, but we're looking at positive x's, so it's this. Do you agree that this is the domain we're interested in? Good. Okay. So now we want to integrate the function arctan of y over x over this domain D. Solution number 1, do you see that D is a simple domain? Right? So you can try expressing D as a simple domain. Suppose you want to take it as simple in this direction, where you take the arrows going this way. So you fix x between, you have to calculate the value of this point. That's going to be your A for the x. You have to calculate the value of this point. These are just intersections of two functions. That's not hard to find. And then the bottom function is going to be this and then this. And the top function is going to be this and then this. Do you agree? And you have to carefully break it into subdomains. So between here and here, it's going to be, the bottom is going to be this thing, and the top is going to be this thing, right? And then between here and here, these 2 points are not one over the other, right? One is slightly more to the left. So between here and here, the top is going to be this circle and the bottom is going to be this circle. And then finally, between here and here, the top is going to be the outer circle and the bottom is going to be y equals x. Probably doable, looks rather tedious, right? Can we do it differently? Yes, we can. Solution B. Solution B is going to be, let's do a change of variables. So what kind of change of variables do I want to do? I want to express this domain D instead of in x and y, in some variables u and v. And in fact, in this example, they're not going to be u and v. I'm going to call them r and theta. Okay? And that hints that I want to use polar coordinates. Okay? We have encountered those before, for example, when we calculated limits, remember? Okay? So let's change to polar coordinates. We know how to do that. We know how to transfer each point x, y to a point r theta. Do you agree? So let me remind you how we do that. So x is going to be r cosine of theta, and y is going to be r sine of theta. That's how we convert points x and y into points of the form r and theta. Right? Everybody remember this? And I want to rewrite this. So you all remember this, right? But I want to rewrite it not just x equals r cosine theta, but x of r and theta. So x is a function of r and theta, and y of r and theta. Okay? So given an r and a theta, we get a new point x and y, and we can write it the other way, right? If we know r and theta, if we know what x and y are, we can find r and theta. R is the root of x squared plus y squared, and theta, hint, hint, hint. Do you remember what theta was? Arctan of y over x. Okay, let's see what happens. So first of all, we're not transferring the entire plane. We want to transfer just the domain D, right? So how does the domain D transfer under this substitution? So do you agree that for this domain D, every point in D, its r is between 1, that's the radius of the inner circle, and 2, that's the radius of the outer circle. All the points in this ring here have their r's between 1 and 2. Do you agree? Do you see that? Okay. So when we transfer D, let's write it here, for points x, y in D, we have that r is between 1 and 2. All the points in D have their r's between 1 and 2. And what about theta? Their theta is between the angle that this line makes with the positive x-axis, this angle, and between this angle, between this theta and this theta. Do you agree? What's the theta for this line? 45 degrees, but we're grown-ups. No degrees in this course. Pi over 4. And theta has to be greater than pi over 4. And between this theta. What's this theta? This theta is the theta that corresponds to y equals root 3 of x, or y over x equals root 3, right? Or, so what's the theta? It's arctan of y over x, so it's arctan of root 3, which is what? Okay, 60 degrees is true, and pi over 3 is even more correct. Do you agree? Do you agree that restricting theta to this interval and r to this interval gives us precisely the domain D, precisely those points? Does everybody see that? Good? Okay. Do you agree that in the r theta plane, when our coordinates are r and theta, this domain transfers to a rectangle? R is bounded between 1 and 2. Theta is bounded between pi over 4 and pi over 3. Nothing is more fun than doing a double integral over a rectangle. Okay, that's arguable, I agree, but that is fun. Do you agree? It's easy, right? It's a very simple domain. You can do it in whatever order you like. There are no functions sitting up there and down there in the snakes. Very easy, okay? So this double integral is going to change to a double integral over a domain E in the r theta plane, which is the rectangle r between 1 and 2 and theta between these two bounds. Clear? Okay, good. Now we know what E is going to be. What about the function? What's arctan of y over x going to be? If y is this and x is this, what's arctan of the product? It's this over this. So the r's cancel. We get sine theta over cosine theta. Right? So we get tangents of theta. So arctangents of theta is just theta. And we knew that. We know that arctan of y over x is theta. Right? That's the change of variables. Do you agree? So this integral is going to change to the integral on this new domain of theta, dr d theta, but there's still one more tiny thing missing. Let's look at the theorem. It's still here on the board. Forget the blah blah for a second. We'll deal with the blah blah in the next clip. We're just doing examples now. So the double integral of f converts to the double integral on the new domain. Good, it's a rectangle. We're going to easily write it as iterated integrals. The function is going to be theta, dr d theta, but we're missing the Jacobian. We have to calculate the Jacobian. And the Jacobian is going to be dr theta, dxy to dr theta. We're going to have to plug in these partial derivatives. Okay? So let's calculate the Jacobian. So calculating the Jacobian for r theta, for polar coordinates. So what do we need? J is going to be the determinant, the 2 by 2 determinant of the old variables, x and y, partial derivatives with respect to the new variables. So the derivative of x with respect to r, the derivative of x with respect to theta, the derivative of y with respect to r, the derivative of y with respect to theta. Right? Let's see what we get. X was r cosine theta. What's the derivative of r cosine theta with respect to r? Cosine theta. What's the derivative of r cosine theta with respect to theta? Minus r sine theta. Y was r sine theta. The derivative with respect to r is just sine theta. And the derivative of r sine theta with respect to theta is r cosine theta. Good? Everybody? Okay. How do we calculate this determinant? Well, that's rather straightforward. It's r times cosine squared minus r, so plus r, times sine squared. So it's r cosine squared plus r sine squared. And cosine squared plus sine squared is 1. So what we get here is just a nice and friendly little r. Good? Now you don't have to run through this calculation every time you change variables to polar coordinates. Okay? We did it once. Now you can use it. Okay? Not that it's hard to redo it, but you can use it freely. Okay, good. So now we can calculate the integral. Let's calculate the integral. The integral, the double integral on our domain D of the function arctan of y over x equals, by the change of variable theorem, to the double integral on the new domain E. But the new domain E is a rectangle, so I'm straight away going to write it as a iterated integral. The integral from 1 to 2 dr. The integral inside is going to be from theta equals pi over 4 to theta equals pi over 3 d theta. Right? That's E. That's the new domain in the r theta plane. Good? The function was arctan of y over x. Oops, I forgot the x and dy. dx, dy. Arctan of y over x is just theta. And we need the Jacobian in absolute value. The Jacobian was r. It's always positive, right? R is the distance from the origin. So we just write r. This is what we have to calculate now. Good? And this is obviously much, much easier to calculate than the original integral, which was not trivial, not in the sense of the function, and not in the sense of the domain. Okay, here some work was going to be required. Whether or not it would converge to a solution, that still remains to be checked, but I'm not going to do it. I'm going to do it this way. Okay? So what do we get? This is a very easy integral to calculate. So let's leave the integral from 1 to 2 dr untouched. We start from the inside. So what's the antiderivative of theta times r? Right. Theta squared over 2 times r, evaluated between theta equals pi over 4 and theta equals pi over 3. Right? So when I plug in the values, I get the integral from 1 to 2. Theta squared, when theta equals pi over 3, so it's pi squared over 3 squared, which is 9, and then over 2, so it's over 18. Minus, when we plug in pi over 4, we get pi squared over 16 over 2, so it's minus pi squared over 32. And all of this times r dr. Good? And after you solve the integral in theta, there better be no thetas around. Okay? Good. All of this is now a constant. We can pull it out of the integral, and we have just the integral of r dr. So it's this constant, which we can write as pi squared, and then we have 1 over 18 minus 1 over 32. Okay, let's leave the common denominator for the next step. And then we have the integral from 1 to 2 of r dr, so it's r squared over 2 evaluated between 1 and 2. Do you agree? So we get what? When we plug in a 2, we get 4 over 2 is 1. We plug in a 1, we get 1/2. 4 over 2 is 2. We plug in a 1, we get 1/2. 2 minus 1/2 is 3/2, so 3 over 2. So we have, okay, pi squared times 3 over 2. And what about the common denominator here? This has yuck. What's it going to be? This is 4 times 8. This is 3 times 6. What? No, only 7 over 288. That's what this thing comes. Really? Okay. And then what is 3? The 288 is divisible by 3. So what is it? 96. 96. So 2 times 96 is 192. So we have 7 pi squared over 192. Yeah, that's correct. Good. Good. Clear? Everybody good? Okay. So here's where we did the change of variables. Okay. We didn't look into the details of the theorem, but nevertheless I want to verify that they hold. Okay. If they don't hold, then we can't use the theorem. Okay. So what were the requirements of the theorem? We did everything, all the technicalities involved. We calculated the Jacobian, we plugged it in, we changed the domain D to the domain E and everything. But let's look again at the theorem. The functions have to be C1. That's easy, right? It's r cosine theta and r sine theta. Those are C1 functions, right? They have to define a one-to-one map, okay, a one-to-one correspondence between the domains. Let's look at what the domains were. The domain in the D variable, in the xy variables was this thing, and we transferred it to the rectangle. We transferred it to the rectangle E. E was the rectangle where in r and theta, r was between 1 and 2, and theta was between pi over 4 and pi over 3. Do you agree? This was the domain in r and theta. Maybe let's write it a bit more carefully. So here's the r theta plane. This is theta, and this is r. And r was between 1 and 2, and theta was between pi over 4 and pi over 3. And our domain was this rectangle. This is E. Right? Everybody with me? And is this correspondence one-to-one? What is a one-to-one correspondence? Can two different points here be sent to a single point here? And that can't happen. This r theta business is unique on this domain. Do you agree? For every point xy, we get one and only one point r theta here, and vice versa. Okay? That's not always true for this change of variables. So if, for example, we were to transfer, let's say, maybe I'll write it as a separate remark. Okay? But in this case, do you agree that each point here, where theta is between pi over 4 and pi over 3, and r between 1 and 2, each point transfers to a unique point in E. Do you see that? Okay. Okay. And the final condition of the... I'll remark about this. This is not an entirely trivial observation that you just always do. Sometimes it doesn't even work, even for this. Okay, so you're going to think about it between now and the next clip. Why is it not always true that this change of variables is always one-to-one? It's not always true. Okay, and one more thing we have to check in this theorem is that the Jacobian is non-zero. Okay, what was the Jacobian? R. Is R always non-zero? Well, R can be 0, but R can only be 0 at the origin, right? That's when R is 0. And for our domain D, R is not 0 because R is between 1 and 2. Do you agree? Okay, so in our case, the Jacobian is not 0 in our new domain, in the rectangle where r is between 1 and 2. Okay? However, remember that we had a remark that we can allow the Jacobian to be 0 at a single point. That doesn't collapse the theorem. So this change of variables would work even if we're looking at a domain that does include the origin, because then the Jacobian would be 0 only at a single point, and that's okay. Okay? It's not relevant to this example, but it's relevant in general. Clear? Okay, so all the requirements of the theorem hold. Therefore, the change of variables which we did here was legitimate, and therefore the calculation by which we got this number is in fact the number that is the double integral of arctan of y over x over that part of the ring. Clear? Good? Okay, so in the next clip, I want to do another example, a bit more involved than this example. This was rather straightforward and easy. I want to do another example in the next clip, and we still have some theoretical issues with the theorem which we want to resolve. That's going to be in the following clips.